Good morning, class. We are looking at Chapter 5, Integral, Section 5.1 to 5.3, the fundamental theorem of calculus. And we're going to continue to get into the substitution rule. Now, the derivative of kx is k, where k is a number, therefore the integral of k dx must be kx plus c. The derivative of x to the power of n is n x to the power of n minus 1. The integral of that is x to the power of n plus 1 over n plus 1. And we discussed the methodology. If you look at the differentiation, we multiply by n, we subtract 1 from it. The reverse process is good this way. So instead of subtracting, we're going to add 1, becomes n plus 1. Instead of multiplying, we're going to divide. And as you recall, we differentiated the right side and we proved this x to the power of n. Couple more. If the derivative of e to the power of x is e to the power of x, then the integral of e to the power of x dx must be e to the power of x plus a constant. If natural log gives us 1 over x, the integral of 1 over x dx must be natural log and a constant. If the derivative of sine is cosine, the integral of cosine x dx must be sine x plus c. If the derivative of cosine is negative sine, the integral of sine x dx must be negative cosine x and a constant. Trigonometric functions will do the same class. Constant multiple rule, sum and difference rules, which basically say we differentiate and integrate both term by term. When you have an exponential, the differentiation we have to multiply by k by the chain rule. For integration, we have to divide by. Now, 5.1 to 5.3, the fundamental theorem of calculus, the method of exhaustion. Areas of a familiar polygon, such as triangles and rectangles, enable us to find the areas of more complicated regions by filling the region with increasingly smaller elements of known area. This is called the method of exhaustion. As you can see in the old days when they didn't know the area of a circle, a equals pi r squared, they would put in there 3-sided, 4-sided, 5-sided, and so on and so forth. As we add to the number of sides, the area of that polygon gets closer and closer to the actual area under the curve, known as the method of exhaustion. What if we want an area under this curve where we have no geometric shape and therefore no geometric formula? What is this area problem? Find the area of the region S that lies under the curve y equals f of x from A to B. This means that S is bounded by the graph of a continuous function f, it has to be continuous, where f of x is positive, is above the x-axis. The vertical lines x equals a, x equals b, and the x-axis, which has the formula y equals 0. This whole thing can be explained by the following. S represents the set of pairs x comma y such that x is between a and b inclusively, and y is between 0 and f of x inclusively. So, how do we find this area? The method of exhaustion. We cut it into so many rectangular strips, and the formula that we use is the Riemann sum, summation of f of x sub I delta x as I goes from 1 to n. That means f of x of 1 times delta x all the way to f of x of n times delta x, where delta x is b minus a over n. Delta x is this width. So it's the same for all of them. Okay. Now, you can choose the width to be anything. They don't even have to be the same because we are approximating. And as far as the height is concerned, you may choose the left endpoints. So that would be the height, for example, if we go with the left endpoints. We may choose the right endpoints. We may choose any point in between. This is not the area under the curve. This is an approximation. To make some sense out of this, we are going to look at this example. And again, you have all of this in your notes. Just understand the concept. Determine the area between f of x equals x squared plus 1 and the x-axis on the interval of 0 to 2. In other words, we want to determine the area of the shaded region as follows. This is class the function y or f of x equals x squared plus 1. Remember, y equals x squared, shifts up by 1 unit, ends up here, right? You follow what I'm saying? And we are going to limit it to what we want from 0 to 2 because it's easier to illustrate it that way. So first, understanding what we are interested in. We want to find this area, and it's not a geometric shape we are familiar with. We are going to guesstimate it as follows. We are going to go with 4 rectangles, which means from 0 to 2, we're going to cut it into 4 equal parts. That's why delta x, b minus a over n is 4. Those are the 4 rectangular strips. N is 4, delta x is b minus a over n, 2 minus 0 over 4, 1/2, or 0.5. That's why we have 0.51, 1.52. So if we choose so the width is fixed, 0.5. If we choose the right endpoints, looks like that. Clearly, that's not the area under the curve, but it's an approximation. So we're going to call it R sub 4. R stands for the right endpoints. So we have 4 rectangles. We chose the right endpoints to represent the height. So for the first one is f of 0.5. For the second one is f of 1. For the third one, f of 1.5. This is function y equals f of x. For 2 is f of 2. Now, what is f of 1/2? If I put 1/2 here, I get 1/4 and 1. I get 5/4. What if I choose 1? 1 squared and 1 gives me 2. 3/2 squared 9/4 and 1, 13 over 4. 2 squared 4 and 1 is 5. This is what we get. Or you can just factor out the 1/2. And when we add them up, we get 5.75. Now, what if we chose the left endpoints as the height? It will look like that. Okay. Again, this is not the area under the curve, but it's an approximation. And we calculate this. First, I want you to notice these 2 parts are the same because the right endpoints uses all these endpoints except the first one 0, and this one uses all these endpoints for the height except this 0.2. And that's why these 3 are the same. And if you want to calculate it by hand, it's easier if you notice that you don't have to repeat yourself and plug in, evaluate, and therefore the area, when we choose 4 rectangles, is between these 2 numbers. But I want you to notice the 2 numbers, the difference is 2, is a lot. So if we add to n, the difference becomes smaller and smaller and eventually becomes small enough to be acceptable. Now, when you look at this concept, I want you to look at this line segment from 0 to 2. 0 equals A, everybody. And 2 equals B. The first endpoint is A, the second one is B. And in between, we decided to go with 4 and therefore 0.5 or 1/2. So 0.5, 1, 1.52. Notice for the height, we use the functional value at all of this except the first one for the right endpoint. So f of 0 is not there. This one, f of 2 is not there. Okay, because we are using the left endpoints. Now we're going to repeat the same question. but this time with 8. So delta x becomes smaller, 2 minus 0 over 8, or 1/4, or 0.25. And as you can see, it looks better already. So we plug in 1/4, this is delta x, f of, you use all of these endpoints except the first one, f of 1/4 or 0.25, f of 0.5 or 1/2 or 2/4, and the rest of them, you put it into a calculator, it gives you 5.1875. We repeat the same thing for the left endpoints. And again, notice most of it are identical. So when you're doing it by hand, for this one, you need f of 2. That means f of b. For this one, you need f of 0. That means f of a. The other ones don't repeat them. You get the answer. And therefore, when n is 8, area is between these two, 4.1875 and 5.1875. So you notice for n equals 4 from the previous page, it was between 3.75 and 5.75, the difference of 2. Now the difference of 1. So clearly the approximation is getting better. The approximation gets better as n gets larger. This is an increasing function and it's concave up, CU concave up, increasing concave up. Right endpoints will give you a larger area. It's called overestimating the area. On the other hand, this one will have an area less than the actual area. It will underestimate the area. That's why sometimes they, in essence, combine them. They use the midpoint. So that's the synopsis of understanding this concept. Now, so chapter 5, integrals, 5.1 to 5.3, the fundamental theorem of calculus. Suppose a continuous function f is defined on the interval of a to b. If the interval is divided into n subintervals so that delta x is b minus a over n, x sub 0 is a, x sub 1 is a plus delta x, x sub 2 is a plus 2 delta x, all the way to the end, x sub n is a plus n delta x, which is equal to b. Then a Riemann sum associated with f is the summation of I going from 1 to n of f of x sub I delta x. So f of x sub 1 delta x all the way to f of x sub n delta x. Again, notice this one is not used for the right endpoints. This one is not used for the left endpoints. And x sub I can be any point in between. So the geometry and procedure is that you cut this a to b into a few, your choice, for example, unless they give you the n. So n is 4 subintervals. And you make up 4 rectangles. Delta x is b minus a over 4, and you have 4 heights, f of x sub 1, f of x sub 2, f of x sub 3, f of x sub 4. Then you make it into more, 8 rectangles. And as the number of rectangles increase, the approximation gets better. For example, for the 4, a is approximated by f of x sub I delta x as I goes from 1 to 4. We use the left endpoints, the right endpoints, the midpoints. They are all approximations. And you don't have to memorize that formula. You just write that line segment that I mentioned and work with that. When we take the limit of this expression, the limit of the summation of I going from 1 to n of f of x sub I as n goes to infinity times delta x, this becomes exactly the area under the curve where delta x is b minus a over n, x sub I is a plus I delta x. This is pretty involved. It's just like the definition of differentiation, which is involved, and then it becomes easier when we use the formulas. The same thing here. This is involved. We use the formulas for that. And so what are we talking about? The formulas FTC, fundamental theorem of calculus, short FTC, and it applies to a function which is continuous from A to B. So what is FTC? There are 2 of them. One of them, and in no particular order, Says ddx of the integral of a to x f of t dt is f of x, meaning if you integrate f of t dt from any number, a fixed number, a constant to x, and then you differentiate it, you get f of x. The other one says, and that's what we are going to use mainly, the integral of a to b f of x dx, which is a definite integral, and it's a number. It's capital F of b minus f of a, capital F of a, where capital F prime equals lowercase f of x. We will make more sense out of this shortly. So let's see what we are dealing with here, class. The integral of a to b f of x dx, this is the definite integral. And what does it mean? Number one, let's look at each piece. This is the integration symbol. As you recall, the symbol was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. Lower limit of integration, upper limit of integration, integral, variable of integration, also known as dummy variable. It is called a dummy variable because the answer does not depend on the variable chosen. The dx simply indicates that the independent variable is x. The integral of a to b f of x dx is a number. It doesn't depend on x. We could use any letter in place of x without changing the value of the integral. So the integral of a to b f of t dt, the integral of a to b f of x dx, or the integral of a to b f of theta d theta, they give us the same number. Its approximation, the integral of a to b f of x dx, is this summation, the Riemann sum I going from 1 to n of f of x of I delta x. This sum is called a Riemann sum. And if you take the limit, the precise value, a equals the limit of summation of I going from 1 to n f of x of I delta x as n goes to infinity, you take the limit. That is the exact value for this, which represents the area under the curve if f of x is a positive function and it represents the difference of areas if it's not necessarily positive. All right, here's a simple example. We want to evaluate the integral of 3 times dx from -2 to 5. And we want to use the concept of areas. So first and foremost, notice the function y, or f of x, is 3, which is a horizontal line. And we want to plot that from -2 to 5. So this is the function y equals 3, and the y coordinate is always 3. So from -2 to 5, -2 comma 3, 5 comma 3. So this definite integral represents the area of a rectangle of width 5 -2, or 7, and height 3. We are looking at this one. So this rectangle has the height, which is fixed 3, right? The height is 3. And this one 5 -2, or 7. Therefore, using the width times the length, 5 -2, 7 times 3 equals 21. Just a simple geometry. Okay, everyone? Just a simple geometry. I hope everybody is okay with that. What if we want to use the fundamental theorem of calculus that says the integral of a to b f of x dx is capital F of b minus f of a, as long as we integrate this? So 3 gives us 3x with only the constant, because the constant will go away, from -2 to 5. So plug in 5, plug in -2. So we get 5 times 3 is 15. And then 3 times -2 is -6. 15 minus -6 is 21, giving us the same answer, everybody. Very straightforward, everybody. Now I'm going to evaluate and pay attention to the concept of signed areas. Use the signed area to interpret interpretation of the definite integral to compute the integral of -1 to 2x dx. So immediately the function y or f of x is x. And the interval is -1 to 2. You know this one is a line through the origin. So we want to go from -1 to 2. We want this area and this area. However, this area above the x-axis is considered positive. This is negative. That's why the signed area or difference of areas. That's important to understand, everybody. So this point has coordinates 2, 2. And we're going to use the area is 1/2 base times the height. The base and the height are the legs. Both of them are 2. 1/2 of 2 times 2 is 2. So the area for the green one is 2. The red one, -1 gives the distance of 1 for each leg, half of 1 times 1 or 1/2. And it's the difference between the two, 3 minus 1/2, 2 minus 1/2, or 3 halves, which is the answer. Well, we could use the fundamental theorem of calculus. That means we could integrate this one to get half of x squared. If you plug in 2, you get 4, -1, you get 1. Half of 4 minus 1 is 3, and 3 halves. What did we show in this example and the previous one? Fundamental theorem of calculus works. Areas work as long as we have a geometric shape, we can calculate the area. But if we can't, what do? This will always work, everybody. This will always work. Now graph and use signed areas to show that the integral of 6x dx from -4 to 1 is -45. I highly recommend you try this so you see this concept better. Okay, everybody? All right, let's go with the definite integral and fundamental theorem of calculus. We're going to use this one. So we want x to the power of 7. We want to evaluate it from 0 to 1, which is a number, is 1/8 x to the power of 8. We don't need the constant, everybody, because this is not a definite indefinite integral. This is not uh, a function. This is a number. So 1/8. You plug in 1, you get 1 to the power of 8 is 1. This is 0, and you get simply 1/8. And here's the tip, which is extremely important. Even if we use another antiderivative, in other words, capital F of x plus c, in the evaluation theorem, the result will be the same, because capital F of b plus c minus capital F of plus c, these two cancel each other. So there is no reason to waste time. What about this one? Please understand this is the same as 1 over x. The answer is a natural log. Because the limits are both positive, whether you use the absolute value sign or not makes no difference. ln1 is 0. The exact answer is ln2. If they ask for an approximation, you follow and you put the number of decimals they ask you. In this case, we have the same function, so we have the same answer except different limits. However, you can't use the absolute value sign because if you do, ln of negative numbers don't make sense. They do not exist. They are undefined. So you must keep the absolute value. You get ln1 minus ln2. ln1 is 0. Negative ln2 is the exact answer, everybody. The integral of 0 to pi sine x dx, as you know, the derivative is cosine, but the integral is negative cosine x. And you're going to plug in pi and 0. It's a good practice to keep this negative sign out. You know cosine of pi is negative 1 minus, you know cosine of 0 is positive 1. So you are looking at minus 2 here. This negative outside makes it positive 2. All right, so we are going to continue with practicing more and more of this stuff. Five thirds x cubed minus 4 halves or minus 2x squared plus 2x. No constant is needed from 0 to 2. So you plug in 2, you plug in 0, you evaluate it. This is the only calculus step, everybody. So let's plug in 2. 0, because each one involves 0 gives you 0. So let's plug in 2, 0 gives you 0. Now, what is this? This is 8. This is 4 minus 8 plus 4. So this is 40 thirds minus 4. And 4 is what? 12 thirds. 4 or 12 thirds. 40 minus 12, 28 thirds. That's the final answer. So pretty straightforward class. This gives us 4v cubed. This gives us minus 3. So first we do algebra. This is v to the power of 4. This is minus 3v from 1 to 2. So we're going to plug in. We plug in 2 to the power 4 minus 3 times 2. Minus, you plug in 1. So just plug in, everybody. So we get 10 minus negative 2. 10 plus 2 makes it 12. Now, 5 part C says, evaluate this. I hope you remember we did this, but without the limits. You can go back to your notes. So we're going to do this pretty fast. So we're going to cut it into 3 pieces. So the first one is 1. This one is minus 7 times 1 over x. So let's just write this. 1 minus 7 over x plus 2 over x. So we cut it into 3 pieces. This one is 1. This one is minus 7 times 1 over x. I want to make sure that we know what happens here. And this is 2x to the power minus 2. So because we are integrating this and the independent variable is x, so this is x minus 7 ln x. I want to show you what happens to this one. We did this again. I just want to show you again. So 2 over negative 2 plus 1 x to the power of negative 2 plus 1, which is minus 2x to the power of negative 1 or minus 2 over x. And again, if you go back to your notes, we had done this. What we did was plus a constant. Now we are evaluating from 1 to 3. So plug in the upper limit, plug in the lower limit. We are going to give everybody a second. And we are going to evaluate this in a moment. So take a look at what happens when we plug in. So we have 3 minus 7 ln 3 minus 2/3. ln 1 is 0. So this one is 1 minus 2, which makes it minus 1. And now it's plus 1. So we write the first one unchanged, and the second bracket changes to plus 1. So we are going to combine these 3 numbers. So this becomes 9 minus 2 plus 3. We are just taking a common denominator. 10/3 and minus 7 ln 3. This is an exact answer unless they ask for an approximation, and you should always come up with an exact answer and then approximation if need be. I can't emphasize this enough, everybody. Always come up with the exact answer. Another example that was done, and I hope you remember, we got t plus a sine t plus a constant. Now we don't need a constant. We don't need a constant because we are evaluating from 0 to power 2. We are going to plug in power 2 minus, we are going to plug in 0. 0 and sine of 0, they are both 0. So this goes to 0. And you should know sine of power 2 is 1. And again, power 2 plus 1 is an exact answer, everybody. The integral of 1 to 4, 5x squared of x plus 3 squared of x. And we have to use elementary algebra to change it and make it ready for the power rule. So this one is x to the power of 1/2. This is 1. So 5x to the power of 3/2 plus 3x to the power of 1/2. First thing first, we want to make sure we can do the power rule. Now, 5 divided by 3/2 plus 1, x to the power of 3/2 plus 1, plus 3 over 1/2 plus 1, x to the power of 1/2 plus 1. So first, 5 divided by 3/2 plus 1, x to the power of 3/2 plus 1. Second, 3 divided by 1/2 plus 1, x to the power of 1/2 plus 1. We don't need the constant. So what do? We say 3/2 and 1. Okay, let's use let's call it 5/2. 5 over 5/2 is 2. 3/2. 3 over 3/2 is 2. So first we do this. And we want to evaluate it from 1 to 4. So we are going to plug in 1 to 4. So we plug in 4, we plug in 1, and we are going to evaluate this class. And it's just algebra. I just want to go over that to make sure everybody's comfortable with that. Four to the power of 5/2 means square root of 4 to the power of 5. 4 to the power of 3/2 means square root of 4 to the power of 3. And this means 2 to the power of 5, which is 32. And 2 times that is 64. This means 2 cubed, which means 8. And 2 times that is 16. 1 to any power is 1. So you get 2 and 2, 4. Minus 4. The answer is 76. Okay, everyone. A lot of, again, let me just show you, this was the only calculus step class. This was the calculus step. Algebra, 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 algebra. All of these are algebra, basic math, you name it. It's really, there is not much to that. Okay. Example 7, this is number 32 of the review. Water flows from the bottom of a storage tank at a rate of R of t equals 200 minus 40 liters per minute. Find the amount of water that flows from the tank during the first 10 minutes. If capital R of t represents the amount of water that flows from the tank at time t, then the rate of flow is given as capital R prime of t equals lower r of t, lower r of t, lowercase r of t, 200 minus 4t. That means this is the derivative of this function. So the amount of water that flows from the tank during the first 10 minutes follows the definite integral of a to b f of x dx, which is capital F of b minus f of a, is also known as accumulated change or net change. So the integral of lowercase r of t from a to b, or more specifically 200 minus 4t dt from 0 to 10. So this is known as accumulated change or net change. So 200t minus 2t squared from 0 to 10. That's for the first 10 minutes, everybody. So you plug in 10, you get 200 times 10 minus 2 times 10 squared. When you plug in 0, you get 0. And so you have 2000 minus 200, and it's 1800 liters because the rate, everybody, was liters per minute. Okay. In other words, dr dt, right? First 10 minutes. So this is 1800 liters, the amount of water. Example 8, many fish grow in a way that is described by the von Bertalanffy growth equation. For a fish that starts life with a length of 1 centimeter and has a maximum length of 30 centimeter, this equation predicts the growth rate is 29 e to the power minus x centimeters per year, where x is the age of the fish. How long will the fish be after 4 years? And then round. If capital L of x represents the length of fish at age x, then the growth rate is its derivative. L prime of x, or dl dx, is 29 e to the power minus x centimeters per year, and it starts life with a length of 1 centimeter. That means L of 0 is 1. Okay, everyone? That's understanding the problem. In essence, this is an initial value problem. So I'm going to solve this two different ways. So the amount of increase in length after the first 4 years is going to follow the definite integral. So we are going to evaluate the integral of this guy times dx for the first 4 years from 0 to 4. This is the amount of increase, everybody. Now, we are going to work on this. 29 divided by -1 makes it negative 29 e to the power minus x from 0 to 4. So this is negative 29 e to the power of minus 4 e to the power of 0, and this is 1. You put that into a calculator, you raise e to the power of -4, you subtract 1, you multiply by negative 29, and it gives you this number. On purpose, I'm using a bunch of decimals. The initial value, L of 0 was 1, must be added to give, this is the amount of increase. So it has been increased by that much. Originally, it was 1. And now it's this much. And now I pay attention to one decimal and I say 4. Next to it is 6, goes up to 5, 29.5 centimeters. What I want to show you is that the second method quickly. Okay, so this one is finding the amount of increase and then adding 1. Instead of that, if the question is says, okay, how long will the fish be after 4 years, after 5 years, after, I don't know, 6 years, then you don't want to repeat this. Rather, you find the function L of x. And when you find the function L of x with the initial value, you can find the constant. So first and foremost, you want to integrate this, and that gives you the same answer here plus a constant. So this one plus a constant, and it's an initial value, big problem because L of 0 is given. So the advantage of having an initial value is that now we have a way to find the constant. If L of 0 is 1, that means L of 0 is negative 29 e to the power of minus 0 plus c must be 1. And as you can see, e to the power of minus 0 is e to the power of 0 is 1. So this is 1. So you get negative 29 plus c is 1. And that means c must be 30. And so L of x becomes minus 29 e to the power of minus x plus c, which is 30. And now you can plug in any number after 4 years, 5 years, 10 years. So if I plug in 4, I must get the same answer. And I wrote it with this format. Okay, class? And I hope you realize why I did that. I want to make a point. There are 2 ways, and you, if a question requires a few different parts, you want to go this route. It's easier this way. Okay. All right, this is it, class. And if you have a question, ask away. Please understand, next week is a fall break. Everybody knows that, class? Class?
Yes.
Okay. So there is no class next week, and have a wonderful break. Happy Thanksgiving, everyone. I'll see you the following week. Take care, everybody. And by the way, Spot short for student evaluation is available. I appreciate if you do that. Thanks, everyone. You may put your full name, last comma first, before you exit. Take care of yourself. I'll see you next time.
Thank you, Professor.
Thank you. Thank you so much. I appreciate that. Maya, how are you? Did you have a question for me?